ready for takeoff.
Hey, everybody. So we have a lot to talk about, and I'm going to get started. Today we're here to talk about simulated annealing, the most metal algorithm ever. In honor, I'm wearing a shirt from my favorite metal band, Overcast, whose members went on to other pretty great metal bands, Shadows Fall and Killswitch Engage. But this isn't about them. This is about simulated annealing. So my name is Chris. I've been developing software since the late 90s. I currently work as a senior software engineer for GitHub, where I work on open source software supply chain security. I also work on a few open source projects. Most notable is the Annealing gem, which I work on with Luis Escordia, and which we'll see in a little bit. I've also been known to be pretty metal in my older days, or earlier days. But these days, I'm pretty chill. I live in Florida with my beautiful family, seen here, and we raise backyard chickens. I can't talk about the kids' names because they value their privacy, but I can talk about the chickens. On the left is Peppa, and then there's Peggy and Millie and Cindy. You might say that these days I've settled into my lowest energy state. Don't worry, that joke will make sense in about 20 minutes. So, simulated annealing is an algorithm designed to find approximate solutions to complex optimization problems. In this talk, we'll introduce what optimization problems are. We'll learn why we might want an approximate or good enough solution to one. And then we'll go through a real-world example of an optimization problem. And finally, we'll see how I use simulated annealing to solve that problem. So let's start out by what is an optimization problem? In mathematics and computer science, an optimization problem involves finding the best or optimal solution from all potential solutions based on some objective cost function. We're going to be talking about two subclasses of optimization problems in particular. One are combinatorial optimization problems, which deal with finding the optimal arrangement of a set from all potential arrangements of a set. And then constrained optimization problems in which one or more of the variables to the problem have constraints which, when not met, may prohibit a potential solution from being accepted or penalize it via the objective cost function. A classic example of a combinatorial optimization problem we can use to demonstrate is the traveling salesperson problem. The problem has several variants, but a simple version can be stated as, given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and then returns to the origin city? So let's say you're an edgy metal crossover band who happens to be software developers, and you're sitting in a pizza shop and you're planning your next tour, and we have a list of 8 cities that we want to visit, and we have a list of the distances between all those cities. In this case, the potential solutions are all of the permutations or arrangements of those cities, which each constitute a potential route. And the optimal solution is the arrangement of cities where the sum total of distances between them is the shortest. To solve this problem, we need to make a list of all of our potential routes, sum the total distances for each route, and then select the route with the shortest possible distance. We might define a cost function that looks like this, which accepts a potential route, then tacks the starting city onto the end to make a round trip, and then totals up the distances between each city based on our matrix table. And then we can use it to find the optimal route like this. First, we gather a list of all of our cities. Then we find all the permutations of those cities as our potential routes. Ruby's has this built-in permutation method that makes that really easy for us to do. And then we loop over all of the potential routes. For each one, we find the total distance along the route using our cost function. And then we compare the current potential route to the best route that we've previously selected, and then we keep the one that has the shortest distance. And at the end, we end up with the shortest possible route, which would leave from any city and follow this path for a 6,900-mile round trip For example, we start in Atchison, Kansas, go to Castle Rock, Colorado, San Diego, Milpitas, then Sturgis, South Dakota, Leominster, Massachusetts, Norwich, Connecticut, Delray Beach down in Florida, and then finally back to Atchison, Kansas. We have fame and glory, and they're within our reach. Just for fun, here's the least optimal route, which is a 15,000-mile route. So if the goal of an optimization problem is to find the optimal solution, why would we ever want to accept an approximate solution? One common issue with optimization problems is they tend to not scale well. The formula we can use to calculate the number of permutations of a list, or the number of different ways to arrange them amongst themselves, is n factorial. And a factorial just means that you multiply all the positive integers that are less than or equal to, between that number that are less than or equal to n. So with 8 cities, there are 8 times 7 times 6 times 5 times 4 times 3 times 1, or 40,320 potential routes to consider. If we have that number of cities and we decided to only visit 4 on our tour, then there would be 24 possible routes to consider. But if we double it up to 16, then there are nearly 21 trillion routes to consider. On my M1 laptop here, it took about 150 milliseconds to run the script we showed earlier on the 40,000 permutation route for the 8-city tour. That scales up to about 270,000 routes per second. So assuming that rate remains linear, and if we ignore any other resource constraints, it would take about 2.5 years to find the optimal route through 21 trillion potential routes for a 16-city tour. In computer science speak, that means this algorithm is NP hard, and this is a super simplified explanation of that because we're not going to go down that rabbit hole. But that just means that it scales in such a way as to eventually make solving NP hard problems impossible. So here's an interesting sidebar for math nerds. With a set of 100 items, there are 9.3 times 10 to the 161st permutations to consider. We know from the map that the route is a loop, and so we can leave from any city along the route, and the distance back to the start will be the same as if we left from any other city. So for instance, going A, B, C, D is the same as going B, C, D, A, and C, D, A, B, etc. So if we remove those equivalent routes, we end up with 9.3 times 10 to the 159th permutations to consider. That's some small progress. Since we can travel a loop in any direction and have it be the same distance, so A, B, C, D is the same as D, C, B, A, then we can subtract those equivalent routes as well, which leaves us with 4.6 times 10 to the 159th potential routes. But, and this is a huge but, while we can figure out what those numbers are really fast through our equations, reducing that real set of 9.3 times 10 to the 161st permutations down to any of those subsets is each an NP hard problem on its own. We can figure them out through brute force on very small groups, but they become increasingly more difficult with larger groups until it becomes impossible. I wrote a test script to try this out, and I can compute the unique pairs of a group of 8 in 600 milliseconds, but a group of 10 members takes 340 seconds. So we can already start to see the problem scale. So we're stuck with searching through permutations, and now back to where we left off. We have 16 cities, we have 21 trillion potential routes, which would take 2.5 years. And now consider that our problem was pretty naive. It assumes straight line travel between the cities and considers only distance as a factor. Our metal band has signed a recording contract after that last tour, and we have some money to plan a larger tour. There's another more practical version of the traveling metal band problem that we could consider. Given a list of cities and a means of calculating the cost of traveling between each pair of cities, what is the optimal route that visits each city exactly once and returns to the origin city, minimizing the total cost? So here, the distance between cities is likely still a factor, but the optimal solution now must take into account the cost of traveling that distance. And while the problem doesn't explicitly state what is factored into those costs, we can make some general assumptions. For instance, maybe it's the airfare between each city, including daily differences in pricing. It could be whether parts of the route would be cheaper to travel by train or car, or the windows in which our fans are available or the stadiums are available to minimize our overnights. And then there might be some limiting factors as well, like how long we want to be on the road before we return home, and the maximum amount the record company is willing to pay. So given these factors, it's now become a constrained combinatorial optimization problem because we have some factors that would disqualify certain potential routes. And now for every permutation of each route, we would also need a way to determine how cost-effective this route is, perhaps based on some historical data, as well as possibly disqualifying some of the routes if they fall outside of our limits or penalize routes if they result in the band being gone too long. Calculating all of that for each route is likely to add some overhead to our processing time, which in turn will affect the rate at which we can process routes. As you can see by now, each variable we add increases affects the number of potential routes we need to consider, often exponentially or factorially. And then each constraint we add increases the difficulty in determining if one potential solution is better or worse than another. Now, given enough complexity, it eventually becomes impossible to find the optimal solution with our available resources. When that happens, we must instead consider if it would be better to have no answer at all or to settle for an approximate solution that can be found with our available resources and that still satisfies our constraints. The traveling metal band problem served us well as a primer for optimization problems, but it's pretty academic and not that exciting. So let's switch from a theoretical optimization problem to a real-world problem that I came across, and then we'll see how simulated annealing can help us solve for it. So over the last 10 years, GitHub has seen its user base increase from 2.8 million in 2012 to 94 million today. Our company size has grown at almost the exact same rate over those 10 years to meet demand. Today, it's a very large organization with several thousand employees, and if you're a new hubber, it's pretty easy to feel like you're a tiny fish in a big ocean. About 3 years ago, a colleague of mine, Max Beiser, had recently joined GitHub and was looking for a way to make the ocean seem smaller by getting to know more people across the growing company. He came up with the idea of forming this special group that anyone could join, and then once a month, everyone in the group would be arranged into random pairs. Each pair would then schedule some one-on-one time to get to know each other better, either via video chat or going for coffee if they were local, or just through asynchronous chat. Other groups soon followed, and each group can configure their own grouping schedule if they wanted to meet more or less frequently than monthly, as well as custom grouping size if they didn't want to just use pairs. Initially, we used a third-party product to help facilitate these pairings, but after a while, we decided to bring it in-house. So Max and I, along with another colleague, Christopher Fuentes, volunteered to write an app to manage these groups. At the time, I remember thinking, how hard could it be? It's just shuffling arrays. Our prototype didn't take long to build, and soon our application could grab the membership roster of each group according to its schedule, shuffle it, arrange the members into subgroups, and send introductions. After the prototype had been cleaned up, we started to review the feedback on what employees would want most from this new internal app. The single most requested feature was to make sure that introductions were unique, even across groups. So if we had two employees, user 1 and user 2, and both members of two groups, group A and group B, then they wouldn't want to be introduced in group B if they had already been introduced in group A. That sounds an awful lot like a combinatorial optimization problem. If we looked at this from the viewpoint of a single group, then the list of potential solutions are every possible arrangement of those groups' members into subgroups of size R. And then the optimal solution is any one of the arrangements where none of the subgroups contain members who have met before. An interesting property of this optimization problem is that in a group of members who have never met before, then all potential solutions are optimal solutions. However, this is not as beneficial as you might think. We learned earlier that you can compute the number of ways that a set of items can be arranged into using n factorial. Given so many potential optimal arrangements in large groups, we might be tempted to write a simple algorithm for dealing with a group of this size that would just keep shuffling the members until we find a unique arrangement, which probably wouldn't take too long. But a surprising statistic worth noting, given a group of 100 members with 9.3 times 10 to the 161st potential arrangements, can you guess how many arrangements we can make before we start seeing repeated pairs? It's 99. It's always going to be n minus 1. And the reason for this is because any member of any given group can only meet with every other member of the group once before we have repeat pairings. And like before, figuring out what those n minus 1 unique arrangements is another NP hard problem. So all we have is our permutations to search through. And every time a unique arrangement is found, that means that n factorial other potential arrangements are now no longer unique. So we'd have to spend a lot of time looking looking for that 99th unique arrangement of the 100-member group. And even if we could find it, then the next time that they wanted to meet, then there'd be none left, and our until loop to just shuffle and find a unique pair would never exit. Now, of course, all of this assumes that our example group is an exclusive set of members, but in reality, there may be any number of groups with any number of members, and those groups may have some degree of overlap with any number of other groups, and each of those overlapping groups affects the ability to find unique arrangements in all of the others. This is getting really complicated. So let's break this down into some new requirements. Groups may contain subsets, supersets, or exclusive sets of members relative to each other. Each member of each group prefers to be grouped with members that they have not been grouped with before. Given enough time, it is inevitable that every member of a group will eventually meet with every other member of a group, and each member may experience repeat groupings at different rates than other members depending on the groups that they are members of. Given this list, we have to conclude that selecting an optimal arrangement is no longer simply a matter of finding a unique arrangement, even for very large groups. Instead, we should consider a unique arrangement ideal if they can be found, but if not, then we should look for arrangements of members who have met least frequently or least recently. We'll need to define a new cost function to help us calculate this. So this table gives an example of how we might want to consider calculating the cost of subgroups containing any two members, given a history of 5 previous groupings. The top of the recency row, where it says near, represents the most recent pairing, and the bottom, by distant, represents the least recent. To the far left of the favorability row is the cheapest possible history where they have never met before. Sorry. Where they have never met in any of the previous groupings. On the right is the least favorable and most expensive possible history, the one where they've met every time. All of the columns in between represent other possible histories where they met one or more times, and they should each have a cost that scales appropriately as we go from left to right. So let's solve this for a single small group first as a proof of concept. Let's start off with our cost function, which accepts a potential arrangement of members into subgroups. First, we loop over each subgroup using an accumulator function. We find all of the combination of members in the subgroup. The subgroup may already be a pair, but we do this just in case we have a subgroup that has more members than 2. Then for each pair combination, we check to see if they've met before based on current history. And then each time that they've met before, we add a cost that is lower for more distant meetings and higher for more recent meetings. And if they've never met, then the cost is 0. And now we can apply that to our permutations of members. First, we convert the potential arrangement to a list of 2 subgroups based on the configuration of the group. We're assuming pairs here. Next, we call our cost function on this collection of subgroups. If the cost of the subgroups equals 0, that means nobody in the subgroup has met before, in any subgroup has met before. Then we accept it outright as the best grouping since it's unique within current history. Otherwise, we'll check to see if the cost is lower than the current best grouping cost. And if so, we'll promote it to the best grouping. If we start with an empty history and run this about 50 times, then we get a pretty even distribution of meetings over time. That's exactly what we wanted. That worked fine for a 6-person group, but it's already not terribly efficient, and we certainly can't do this for all permutations of a 100-person group. Also, as our history gets deeper, the cost calculations are getting bigger, so we can't really do this unbounded. Sounds like it's time for an approximate solution. After all, these are just friendly hubbers who just want to have a chat, and so precision isn't a hard constraint. I think it's finally time to introduce simulated annealing. So as you may have guessed from the name, simulated annealing is a simulation of physical annealing. Physical annealing is the process of bringing a material, such as metal, up to a certain initial temperature, then letting it cool slowly at a certain cooling rate. This allows the crystals in the metal to traverse through many different states to reform into a more desired structure. When the material is hot, the molecular structure of the crystals is weak, allowing it to undergo big changes in those crystals. As it cools, the molecular structure becomes stronger and less likely to change. The slow cooling rate allows the molecular structure to eventually settle into its lowest energy arrangement. The initial temperature and the rate at which the material is allowed to cool is called the annealing schedule. Now, simulated annealing mimics this process, but the material is the problem that we want to solve. The different states are all of the potential solutions to the problem, and the energy of each state is synonymous with the cost functions that we've seen. The temperature and the cooling rate are used to limit the number of different states that the annealer will sample, as well as deciding how big of a change between states the simulation is likely to allow. Finally, the desired structure is the optimal solution that we can find with the lowest energy arrangement within the bounds of our annealing schedule. So the annealing process goes like this. First, we define an annealing schedule, which is going to be our initial temperature and a cooling rate. Next, we select a random potential solution as the current state of our problem. Then we generate a new solution from the current state to use as our new state. Then we use a cost function to measure the energy of both states. Then we decide which state to keep as the current state. We reduce the current temperature of the annealer according to the annealing schedule. Then we check the simulation limits to see if we're at the end. Otherwise, we go to step 3. So let's plug our problem into the annealer as we walk through how it helps us find an approximate solution. Step 1, define an initial temperature and a cooling rate. Our first step is to define the annealing schedule as the temperature and the cooling rate. The exact schedule we use will differ depending on the problem we're solving, but as a general rule, the starting temperature will be greater than 0, and the cooling rate should allow for the temperature to drop slowly to 0, the slower the better. The temperature can be allowed to cool linearly, geometrically, or even conditionally based on the current state of the simulation. The default is linear reduction in temperature, but the annealer gem does allow us to define a cool-down method if we wish. We're just going to use the default here. Using a linear scale also means that we can easily figure out how many solutions our simulation will consider. 200,000 seems like a reasonable sample size to start with, and we can fine-tune it later. A cooling rate of 0.001 gives us a nice and slow reduction as we go to 0, and an initial temperature of 200 gives us those 200,000 steps. Step 2, select a random solution as the current state. Since we can't predict where the real optimal grouping will be among all of the potential groupings, then any starting point is as good as another. The purpose is simply to give us a jumping off point so we can start to explore. Here we get a list of members we want to group, 1 to 100. Then we create an initial grouping of pairs from the shuffled list. It doesn't necessarily need to be randomized. The initial or default arrangement of the set may be as good a place to start as any. Step 3. Generate a new solution from the current state to use as the new state. We need a way to traverse the problem space, which is all of the potential solutions, in search of an optimal or approximate solution. Earlier, we gathered all of the permutations of a set and then looped over them. Simulated annealing doesn't take this approach because it assumes that there are already too many permutations to explore fully, and so there's no sense in generating them and storing them in memory. Instead, it uses this idea of exploring neighboring states, which can be generated by making the smallest possible change to the current state to produce a new state. This allows us to explore around the current state in depth. You may think that this comes at the expense of breadth, but I'll explain in step 5 why this isn't the case. What we need to do right now is develop a method for making those state changes, all of which will happen inside the simulation. In our case, this might involve exchanging a random member from exchanging random members from 2 random subgroupings. So this function takes the current state and makes a clone of it. Then we find 2 random subgroups from the new state and pick 2 random indexes within each subgroup. And then we just swap those 2 members between the subgroups and return the new neighboring state. Step 4, measure the energy of both states. The energy of a given state is the same as the cost function of the potential solution. We already have this method, so let's plug it in. This is the exact same function we designed earlier, just with the argument name changed. So we won't go through it again, but let's take a minute to appreciate how easy that was to drop in from our earlier brute force attempts. Which leads us to step 5, deciding which state to keep as the current state. Now, you might think that should be obvious that we should always accept the state with the lowest energy, since that's what we're optimizing for. However, if we're only willing to explore in the direction of more optimal, we may get stuck at the bottom of a relatively high valley, even if there are lower valleys to explore. We call these positions local minima, and they can behave as barriers that prevent us from finding the global minima, which is what we're after. We can get around these barriers by occasionally allowing the algorithm to select a less optimal state, which allows us to go in a different direction. The rate at which the simulator will allow selecting a worst state is based on a modification of a probability distribution algorithm known as the Metropolis-Hastings algorithm. We're not going to get into specifics about how that algorithm works, but the result is that our sampling should end up being pretty close in distribution to the full set of permutations. And just like in the physical annealing process, when the temperature is high, then we're more likely to accept a big change, i.e. a worse solution. And then as the temperature cools, that probability collapses, allowing us to settle into a low energy configuration. As I said, this is already baked in. We don't need to do anything special to take advantage of it. Whatever state is selected by the simulator will automatically be promoted to the current state before the simulation continues. So step 6, reduce the temperature of the simulation according to the annealing schedule. We decided in the beginning to use the default cooldown method, so at each iteration of the annealing algorithm, our temperature will be reduced by our selected rate of 0.001. There may be cases where we want to handle this differently, perhaps even raising the temperature under certain conditions, which the annealing gem does allow for. In any case, there's nothing further for us to do here because the annealer handles this for us. Step 7, check the simulation limits, then go to step 3 if they have not been met. By default, the simulation will end once the temperature reaches 0. Sometimes, though, we may want to decide to stop the simulation earlier, perhaps if we found an energy that is under a certain acceptable threshold, or if we haven't selected a worse solution, if we haven't selected a worst outcome in a certain number of iterations. The annealing gem does allow for this. Earlier, we show how we'd want to automatically accept a zero-cost arrangement, so let's add this now. Now, at the end of every iteration, if the annealer will check to see if the current energy reading of the most current state is 0, and will terminate early if that's the case. Otherwise, it will continue until the temperature drops to 0. And now we have everything we need to run the simulation, so let's do it. Here we set up our simulation as an instance of Annealing Simulator. All of the configuration options we added before are automatically inherited. Then we just run the simulation to get our optimal grouping. The optimal grouping, when it's done, will have a state which contains the approximate solution that it could find, and we can read the energy of it to just see how well we did. And that's it. Hopefully by now you understand what an optimization problem is, why we sometimes need to accept an approximate solution to one, and how simulated annealing can help us find one. If you're interested in exploring simulated annealing deeper, I highly recommend that you start with the research paper that introduced it called Optimization by Simulated Annealing, which was published in 1983 in Science magazine. If you're looking for a primer on algorithms in general, finding a copy of Grokking Algorithms by Aditya Prakash is your best bet. And if you're interested in optimization problems in general, I encourage you to check out a tool that I just learned about last week called Google OR Tools, which is an open source suite of software aimed at helping to solve optimization problems. I am not on social media, but if you have any questions or comments, I welcome them at chris@christopherbloom.com. And also, don't forget to check out the Annealing Gem as well. Thank you.